Hi there. In this video, we're going to be looking at what is a directional derivative. So in order for us to understand what is a directional derivative, we first need to understand what is meant by scalar field, vector field, the gradient vector of a scalar field, and lastly, all of this culminates into what we know as the directional derivative. So first things first, what is a scalar field? So a scalar field is just a graph, right? It's just a curve. It's what we've been working with throughout our lives thus far in wherever we've studied maths. So if we have a 3D independent variables, set of independent variables, and of course the fourth dimension is our dependent variable, for example, temperature, right? Or think about some kind of room. So a point in space, x, y, z, corresponds to a certain point in the room, and that point has a certain temperature, okay? So we could generate theoretically some kind of 4D graph from these three variables. So perhaps the most easier way to understand it is to think about perhaps gravity, right? If we think about the Earth, and of course the Earth has a certain radius, okay? And we think about the gravity that we experience. So of course, if we're going to be moving away from the surface of the Earth, then our gravity that we experience is going to be much lower. So the gravity we experience at the surface is much more higher than the gravity we experience further away. Okay, we know that from Newton's laws, the laws of nature, etc. So if we draw this on a graph, where on the x-axis we just plot the radius, and then on the y-axis we plot the gravity that we're experiencing, then it would look something like this, right? And at this point here, we have the radius. So at the radius, we experience the biggest gravity. And then going further away, we experience less gravity. So this is a scalar field. It's just a graph. That's just what we know, okay? So now, how would we show this as a vector field? What is a vector field to begin with? So vector field is not a graph. It's just literally, we have our Cartesian plane or whatever it is the case. There's the Earth again. So what we do is we just showcase a series of vectors. So at the surface of the Earth, gravity is much higher, right? So we have very significant arrows all pointing in the direction of the center of the Earth. So what that means is that in the direction of the center of the Earth is where gravity is the highest, okay? And further away, we experience less gravity. So this is a smaller arrow, like that. And we can carry on drawing this, right? So even further away, we'll have a smaller arrow. So this is an example of a vector field. A vector field is showcasing that in a certain direction, we can have a sequence of arrows that show how something is changing, how something is spread out. On the surface of the Earth, we have a big arrow showing that gravity is very large and all pointing towards the center of the Earth. So there's a variety of different vector fields that we can draw. And the exact same thing is being shown on this graph, which is the scalar field, which is just the case that, you know, at the radius of the Earth, we have a lot of gravity. And then as we move further away, we experience much less gravity. But this does not show direction. That's why this is a scalar field. So scalar field just shows the values, and the vector field shows the magnitude and direction. So there's no curve per se on the vector field. It's just the case that there's a sequence of arrows that shows how big at a certain point, whatever is be the force, be temperature, or whatever, right? But as you move further away, you can see the arrows get smaller, and they show that, okay, you know that this is that direction and this is the magnitude. So that's the difference between a scalar field and a vector field. So if we have a point in 3 space, like a point P that's here, and we have some function phi, and this function is of x, y, and z. So we put in x, y, and z, and we get some value. Think about temperature, right? So at a certain point, it has a certain temperature. Maybe think of your home. Maybe one room is air conditioned and the other room is not. So the one that has air conditioning will be much colder. So where you are depends on where the temperature is. So that would be an example of a scalar field. So with a vector field, each of these different vectors, we can write a vector field as the form, as what we have shown previously, maybe the force of gravity or some force or whatever the vector is. But we have some vector function, x, y, z, right? And that's equal to some x component, some y component, and some z component. So how does this relate to anything? What does this mean now? Okay, so we're going to consider the scalar field first. Okay, so the scalar field is where we're going to find the concept of the directional derivative. So the first thing we want to introduce is the gradient vector. So we have some function, some scalar function that depends on x, y, and z, right? Sorry, that should be a comma. So the gradient function, gradient vector, sorry, we write it as grad of the function. So the gradient vector is equal to just taking the derivative with respect to each component. So we have the gradient vector taken derivative with x, that becomes the x component, and the derivative of the function with respect to y becomes the y component, and the derivative of the function with respect to z becomes the k component. So we have a scalar function, right? And we form from this scalar function a vector. Okay, what does this mean? What is our interpretation of this? So let's just look at the previous example. We saw that, okay, let's just say we have the radius of some planets, whatever it is. Okay, we'll just say as our point of origin is the point of origin is the radius of the Earth. And okay, again, we have the same thing. At the surface of the Earth, we're experiencing gravity, right? So this function on the y-axis is gravity, okay? So what are we saying here? What does this mean? What is a gradient vector? So let's just say this function is a function of r, and it's 1 over r squared, okay? That's what this function is. So let's form the gradient vector of this. What's the gradient vector? Okay, don't worry about r and x and y and whatnot. All we're just considering is g and r. So these are just our two components, okay? So if we find the gradient vector of this function g, okay, what is it going to be? It's going to be, this is r to the minus 2. So finding the derivative of that is minus 2 times r to the minus 3. And since there's only one direction, there's only one x component, okay? And let's just say we compute this gradient vector where r is equal to 1, okay? So the gradient vector where r is equal to 1. So when we do that, we get minus 2. So what does this mean? It means that when r is 1, we have a horizontal vector of magnitude minus 2. There's 1, maybe there's minus 1 here. So we have a horizontal vector pointing like this, in which the magnitude is minus 2. So let's think about this, what this means in terms of the Earth or planet or whatever. So what we're saying is if we are here, right, we are going to experience the greatest change, the most change in gravity if we move like this. If we have a horizontal vector, and if our path is towards the center of the Earth, then that is where we are going to experience our greatest increase in gravity. So this is the interpretation of the gradient vector. So the gradient vector tells us the direction in which we will experience the largest change in that particular function. In this case, it's gravity. So if we move along this path, we will experience the largest change in gravity. So this is what the gradient vector is telling us. So there's a few other things that we need to know, like for example, what is the gradient vector? So just perhaps a few other things before we move on. So this gradient vector is given a symbol. So that symbol is del. So it looks like a triangle like this. So it's called del. So this means the gradient vector. So del of the function is, let's just say a function is phi. So it's just the same thing as the gradient vector. So an important thing to consider is we can only compute the gradient vector of a scalar field. So this function phi is a scalar field. If we say del f and f is a vector, this has no meaning. This is not correct. So this doesn't mean anything. We can only take the gradient vector of a scalar field. So that is something very important to consider. So let's just say we have our normal x, y, z plane, and we have some kind of vector. Say that vector is r, and there is some point P here. And from this point P, this vector r has a change, okay? So it has this magnitude, and there is some change. Call that change dr, right? So if we just draw dr here, then dr has firstly a z component, an x component, and a y component. So we can see it here. That's z, and then this little bit here is y, and that little bit there is x, right? So we can write dr as just having these components dxi, dyj, and dzk. Okay. So now we know that the gradient vector, we'll write it as del, or some scalar function, is equal to day phi dx, day phi dy, and day phi dz. Okay. And what we're going to do is we're going to multiply this gradient vector by this differential change in some vector. Okay. So we're going to multiply this two. We have two vectors and we're multiplying them. What kind of multiplication are we doing? We're going to do the dot product. So we're going to take the dot product between this gradient vector and this differential change in some arbitrary vector. Okay. And when we take the dot product, you would remember that when we multiply I hat by I hat, we just get 1, okay, because those vectors are in the same direction. But when we multiply I by j and I by k, they all give us 0. So what we're going to get is day phi day x times dx plus day phi day y times dy plus day phi day z times dz. Okay, and at this stage you might be thinking to yourself, this looks kind of familiar, right? You've been looking at this in a variety of different ways thus far in multivariable calculus. And yes, it's exactly what you think it is. It's an exact differential. You'd remember in the past, if we looked at just two independent variables, we said dz was day z day x times dx plus day z day y dy, right? Exact differential. So here it's just the case, we have three independent variables. So the four-dimensional function that we're considering. You'll also remember we looked at p dx plus q dy plus r dz. Exact differential, okay? So the whole point of this is that the product of the gradient vector and some random arbitrary differential change in a vector gives us d phi. So the differential change in some function is just equal to the gradient vector of that function multiplied by this dr, differential change in a vector. So let's just write that down. So d phi is equal to gradient vector multiplied by dr. So this is an important result, and we're going to use it now in the following way, right? So just look at our previous graph where we saw, okay, the gravitational function as a function of radius, and we have some curve like that, okay? And then we looked at some arbitrary point, and we saw that the directional derivative, or the gradient vector, sorry, not directional derivative, the gradient vector is something like that, okay? So what we're saying is that if we're going in this direction, we'll experience maximum change in gravity. So let's just say now, instead of going in this direction, I'm not going to go in that direction. I want to go in, let's just say, this direction, okay? I'm going to go in this direction. So in terms of a practical sense, what are we saying here? Practically, if we have our Earth here like this, and instead of moving in this direction, okay, we move in that direction. We're not moving in the direction of the maximum change in gravity. we are moving closer towards the center of the earth. If we move like this, we are moving closer, but we're not moving on the direct path, okay? So how do we compute the change in that? What change in gravity are we going to experience if we move in this direction? Yeah, it's definitely going to be less than the direct path. So how do we compute that, okay? So the first thing we do is that we consider this little red vector that I've drawn. We call it dr, okay? And this vector representing the maximum change, well, that's obviously del of the function, del g. Okay, just for, let's not complicate it any further, we'll just call it phi instead of g. So we can keep the notation consistent, right? So what are we saying here? What we're saying is that we need to now consider what is the change in the gradient vector in this other direction, dr, okay? And what we need to ask ourselves is, what is the rate of change of the function in this direction? And let's just say now we have this direction here, and we have this gradient vector like this. So we have dr, but the length of this curve that it's moving on is ds, okay? So the length of the curve is ds, and the actual vector itself is dr. So that's dr. So we can say that the magnitude of dr is equal to ds. Let's write it here. So ds is equal to the magnitude of dr. So dr is there, that's the direction of the vector we're going in, but the total distance traveled or whatever is ds. And since ds is the same as dr, the magnitude of dr is just ds. So what we're asking ourselves is, what is the rate of change of the function with respect to ds? So the differential of this change, this d phi, we saw just now that it's simply equal to this del of the function, the gradient vector multiplied by dr. So that's what we're going to write. We're going to write the gradient vector multiplied by some other vector, this dr in this other direction, divided by ds, okay? And this is just equal to the gradient vector multiplied by dr over the magnitude of dr, since ds is the magnitude of dr. But this is a unit vector, right? When we take a vector and we divide it by its magnitude, we get the unit vector. So this is now what is the directional derivative. So this d phi ds, right? This is the directional derivative. So it is the directional derivative. So what is it? It is simply the rate of change of the gradient vector in another direction, okay? So if we can think about these vectors that I've just drawn here, I'll just draw it a little bit bigger, okay? So this is our gradient vector, del phi, and this is our other vector dr, okay? And we want to know now, we're asking ourselves, what is del phi in the direction of dr? And you remember when we take the dot product, we're asking ourselves, what is the projection of del phi in the direction of dr? So this directional derivative, d phi ds, okay, is literally just the magnitude of del phi in the direction, the projection, and the projection is cos theta. If you just don't understand this, just look back at our revision video on dot product and vector products and whatnot, and you'll understand this. It's simply just the projection of the one vector on the other vector. It's the scaling of the gradient vector in the other direction. So that's what the directional derivative is. So to compute the directional derivative, all we do is we find the gradient vector, we find the other vector, right? And then what we do is we divide it by its magnitude, and then that will give us what the directional derivative is. So just to summarize once more, the gradient vector tells us, okay, if we go in this direction, we'll experience the greatest change in gravity. So some other vector, we experience less gravity, because even though we're kind of moving closer to the center of the earth, we're not really going to experience the same rate of change of gravity. So we find that answer, we find what is the gravity that we're going to experience by taking the projection of the gradient vector in the direction that we are actually going in. And that what that is we take the gradient vector and multiply it by the unit vector of the other in the direction that we are actually going in. So this method can just be easily illustrated by just a simple example. So we have some scalar function, okay, and that's equal to x squared z plus 2xy squared plus yz squared, okay, and we want to find the directional derivative. So it's the directional derivative at the point 1, 2, minus 1 in the direction of 2i plus 3j minus 4k. Right, so that's what we actually want to do. So you would remember that the directional derivative, it's d phi ds, and it's equal to our gradient vector multiplied by this unit vector here divided by, well, we're writing dr, but it's whether it's dr or r, it's kind of just, we just use dr just to derive it. But whether it's a infinitesimal length dr or whether it is actually a finite length like r, then it's basically the same thing. It doesn't affect our definition in any way. But just to make it consistent with what we've developed this far, we'll just write it as dr over dr. So our first step is to compute the gradient vector, that's del phi, and we can see in our previous what we've done so far that the gradient vector is quite easy to compute. All we just do is we take the derivative with respect to x, derivative with respect to y, and derivative with respect to z. So when we do that, what do we get? Well, taking this term, the derivative with respect to x, we're going to get 2xz, and then there's just x here, so we get plus 2y squared, and there's no x in the third term. And then finding derivative with respect to y, there's no y in the first term. We have y squared in the second term, so we get 4xy plus z squared, taking that term with respect to y, j. And then lastly, first term, we're just going to get x squared. When we take the derivative with respect to z, there's no z in the second term, and then the third term is just going to be plus 2yz. So substituting in our values because we wanted at this point. So we have 2 into 1. Then we have minus 1, which is what z is. Then we have 2 into 2 squared, which is what y is. Then we have plus 4 into x, x is 1, times y, y is 2, plus z squared, z is minus 1, squared, plus x squared. So we have 1 squared, plus 2 times y, which is 2, times z, which is minus 1, times k. Sorry, I forgot I, j, and k. So that's j and that's I. So when we do this, we have 2 times 1 times minus 1, that's minus 2. Minus 2 plus 2 squared is 4. 4 times 2 is 8. So minus 2 plus 8 is 6. I. And then minus 1 squared is just 1. So we have 4 times 2 is 8. And then 8 plus 1 is 9. So I have 9j. And then 1 squared plus 2 times minus 1, that's minus 4. Minus 4 plus 1 is minus 3. Okay, so that is the gradient vector del phi, And now we want to compute the unit vector of in the direction of r. So how do we do that? We can just do it here quickly. So we take the magnitude of r. So that's just going to be the square root of 2 squared, which is 4, plus 3 squared, which is 9, plus minus 4 squared, which is just 16. Okay, and that gives us the square root of 29. So our we'll just write it as r over magnitude of r is equal to basically 1 over the square root of 29 multiplied by the vector r, which is just 2i plus 3j minus 4k. So finally, as the last step, all we just do is we multiply them as per the equation that we've developed. So we just take the gradient vector and we multiply it by dr over r. So the directional derivative d phi ds is simply equal to this 6i plus 9j minus 3k. Then we're taking the dot product with 1 over square root of 29 into this 2 plus 3 minus 4. 2i plus 3j minus 4k. So what is this equal to? Let's go a little bit down. So when we multiply it, remember when we multiply the i's, all we just get is 1. And I times j gives us 0. So we're left with 1 over the square root of 29 into 6 times 2, which is 12. Remember, we're taking the dot product, right? So there's not going to be any vector components left. 12 plus 9 times 3, which is 27, plus minus 3 times 4, which is plus 12. Okay, so this is all just equal to the sum of this divided by root 29. So 12 plus 27 plus 12 gives us 51. So the final answer is 51 over the square root of 29. So this is what